Hello everyone, welcome back to my tutorial. In this tutorial we are going to see static analysis of conducting rod. It has a material of steel with Young's modulus of 210 gigapascal and Poisson ratio is 0.3. And the boundary condition is here the force is coming from the piston of 10,000 Newton in y direction, and here it is connected to the crankshaft. So I'm just to solve this only, I'm just fixing it here. So now we'll solve this problem using a salome. Before that, please subscribe my channel to view similar kind of problems in salome and press the bell button for notification. Now move into the case. So first open the salome, go to the geometry model. This connecting rod I have already created using a geometry model software. Now we'll directly import this model into salome. So here you can see I have modeled the connecting rod. So this is my connecting rod. I have modeled using a cryoparametric. I have saved this file into step file. Now we'll directly open this step file in geometry model of salome. Go to file, import, step, pictures, code aster. So here connecting rod, select this connecting rod file, just open it. Here we have to give S. So after importing any file into the salome, we have to check the dimension. So here I am using a meter unit. So just go to inspection, dimension, bounding box. So this is my dimension which is I wanted. So if any dimension changes, if it is showing in mm or meter, we have to scale down or scale up, we have to do it. Now the dimension which is coming is correct. Just close it. Then we'll create a groups to apply the boundary conditions. So here you can see we have to create two groups. One is surface group of here and surface group of here. So just go to new entity, group, create group, face group. So select this surface as well as press the shift and hold, select this surface, then add it, just make it force, then we just apply it. Then this surface I have to fix it, select this surface, add, fixed x, y, z, then just apply, close it. So to salome, our code aster only apply pressure boundary condition. So this force has to be converted into the pressure. For that we have to calculate the surface area of this surface. For that just select this force group. So go to instruction, there is an option called basic property. The area is this one, just copy this area, just paste it here. So this one is the area value. So applying boundary condition, this has to be entered inside the solver. Now just save this file in the connecting rod folder. Now we'll move into the meshing model to create the mesh. So select this rod, mesh, create mesh. Previously we have used Gmesh for creating the TET mesh. Here I am going to use NetGen algorithm and simple parameter. So if there is small features are there, just go with the 3D parameter, use simple fine, then OK, apply and close, then right click it, compute it. Because if there is any small fillet round is there, it's better to go with the 3D parameter. So wherever small surface is there, it will generate fine element. Wherever the bigger surface is there, it will generate coarse element. It automatically will control. think it is generating more number of elements, it seems. That's why it's taking time. Yes, it is generated more than 55 lakh elements. So it is generated 6,29,000 elements. Just simple component is generated that much of elements. Here you can see that is because of smaller fillet. So here there is a small fillet is there. That's why it is generating that much of elements. Now we can reduce the element size also. Just right click here, edit mesh. Instead of fine, just go with moderate, then just OK, apply and close, and go with clear and compute. Because if you take more number of elements, it will generate more number of nodes. More number of nodes means solving time also it will take more. So now you can see, so just 1,55 elements, only 35,000 nodes are there. So this is enough for our case. Now check the groups also taken into the mesh. Now we can go for aster study to create the setup. Just go to aster study, just save OK. Here also for this skills also I'm going to use the assistant linear elasticity model. So this is the steel material property. Yes, keep it the same. Fixed, here we have to fix it completely, and here we have to apply the force. I'm just giving a dummy force of 1. Then you just save this file. Connecting rod, result.rmad, just save it, finish it. So first we are reading the mesh, defining the model. Here you can see mechanical model, defining the material, assigning the material. One side we are fixing it, other side we have to apply the force. Just go to here, untick this pressure. Here just type force. There are different boundary conditions. We have to choose force phase. We have to apply the force in y direction, sorry, in x direction. So this is negative x direction. So choose the element, force group, say OK. In x, add the variable. So any name I can give, force I'm giving, or for sure we can name it minus, so the value is 10,000 Newton, 10,000 divided by the area. So this is the pressure value we have to apply it to apply the 10,000 force. So because force boundary condition as well as the pressure boundary condition in salome, it will apply only the pressure. So to apply the force of 10,000 Newton, we have to give the pressure value of this much in this surface area. Then just apply and close. Then just OK. Then apply and close. This force variable is added as a negative. Now it is correct. So now we have added everything. This static solver only calculate the displacement. To calculate the stress value, just go to post processing, calc champ, use this one, sigma element and sigma nodal, SAEQ element as well as the SAEQ nodal. Now just apply and OK. Here change this result into calc champ, click this tau champ, make it into S, then just say OK, then apply and OK. Now we have defined everything. Now we can solve this case. Just go to history view, click this plus button, 5 seconds, give some more memory and run it. Now you can see it is solved without any error. Now we can go for a paraview to do the post processing. Go to Paravis. Now we are in the Paravis. Right click this built-in and open. Just navigate into the folder. Now connecting rod, result.rmd, then just apply it. Now we have opened the connecting rod. First we'll see the displacement. So I'm just changing this color into rainbow, blue to red. Just apply and close. And here I'm just making into 12 number of data. So this one is the displacement magnitude. You want to see the displacement in x direction. This is the displacement in x direction. You want to animate it just with the deformed shape. So to see the deformed shape, just go by warp by vector. Just apply it. Now we have given a scale of 1. Increase the scale. Yes. So this is the deformed scale. Go to create a new animation track. Instead of 1300, I'm just giving some 300 scale factor. This is 20 frames. Just say OK. Now we can animate it by using this animation. So we can put the loop also to animate it. So the animation is correct. The applying load direction also correct. Now we can check the stress value here. So SAEQ. This also I'm changing the color into rainbow, blue to red. Apply and close. This data I'm just making into 12. So whatever the data we are seeing, this is the magnitude. And I just go to von Mises. So this one is the von Mises stress. So here you can see, here we are getting more stresses. Similarly here we are getting more stresses. So to see the maximum and minimum value, here also we can check. Find the data. Instead of cell data, we can go for point data. So here what data we just want to see, that is we can choose von Mises data. This is the first one. Maximum value, just select it. Here you can see, here only we are getting the maximum value. Here you can see this orange color it's showing there only. We can give some green also. See, it is showing the green. Purple color. So we cannot view it actually. It's better to give it the orange. So this no issues. This way we can check the maximum value. Similarly, we can check with the minimum value also. So one by one we can find it. So now we are getting around 110 megapascal closer to this location. Now we have solved the static analysis of connecting rod using salome. So please subscribe my channel for more videos and click the bell button for notification. Thank you.